An aquarium uses 20 gallon salt water tank to house multiple species of sea animals, including the octopus right here. Here we got the first tank is 20 gallons, second tank is 20 gallons. They use a 20 gallons pre-mixing tank before dumping the salt water solution into the main aquarium. So we got the pre-mixing tank labeled here in the figure and the aquarium. The pump between the pre-mixing tank and the aquarium operates at 20 gallons per minute, and we have that depicted as well. So let's say that this is the pump, and what else? The salt is added to the pre-mixing tank at a concentration of 2 pounds per gallon at a rate of 20 gallons per minute. So I think this is saying that in this rate of 20 gallons per minute, there's a concentration of salt of 2 pounds per gallon and flows into the aquarium at 20 gallons per minute, and it's depicted here. And water from the aquarium is discarded at a rate of 20 gallons per minute. Okay, so let's say that this is tank A. We want to write the system of equations that model this system in matrix form. So this is the form that we want it in. So the first thing I'm going to do is I'm going to focus on tank A. And we're going to say that the amount of salt in tank A as a function of time is A sub 1. And the derivative of that, that's going to be the change in the amount of salt. So the rate of change of the amount of salt with respect to time. That is to say pounds per minute. So now that's going to be equal to the rate of stuff coming in minus the rate of stuff coming out. So if we're able to decompose these rates, we're on track. So we have 20 gallons per minute coming in. Now we said here we're modeling the rate of change of the amount of salt in pounds with respect to time. So pounds per minute. Here we have gallons per minute. However, we know that the concentration of the rate in is 2 pounds per gallon, which, if you do dimensional analysis, gets you 2 pounds per minute. So we're on track right now. There's nothing else going in, but there is something going out, the 20 gallons per minute. So we're going to write 20 gallons per minute here, and then we're going to say, well, if it's going out, what concentration is it going to have? Well, whatever the concentration of the tank is at a specific time. Well, we already said that we're modeling that concentration in tank A as A sub 1 as a function of time. And, we know the amount is modeled as A sub 1 as a function of time. That is the pounds of gallons. The concentration is the amount divided by the volume. And in this case, we have a volume of 20 gallons plus the 20 gallons coming in per minute times how many minutes has passed minus the 20 gallons going out per minute times how many minutes have passed. But these two offset each other. So we can just look at this. This cancels out. And here we get A sub 1 prime is equal to minus A1. I'm writing the second term first plus 40. And I drop the units for simplicity. Now we're going to do the same process for the tank B. So let's say we use this color and we say this is tank B. Tank B is going to have a concentration, but we're not going to measure concentration right now. We're going to say that the amount of salt in tank B at any one time, that is in pounds, the pounds of salt at any one time t, is modeled by A sub 2. Now, the derivative of that is going to be the pounds per unit time, and we're using minutes for time. So we're using basically the rate of salt, the rate of change of salt. And that's going to be A prime sub 2. That's going to be equal to the rate in minus the rate out. Now, what is the rate in? Well, as you see here, we got 20 gallons per minute going in. But we said again that we are modeling the derivative of the amount of salt in pounds with respect to time. So that is pounds per minute. Here we have gallons per minute. So we have to multiply it by pounds over gallons, which is the concentration of the salt of this water right here? Well, that's coming from A. So it's whatever the amount in A1 is at any one time, and we're modeling that function, divided by how many gallons we have in A, which is 20 gallons because I said the gallons coming in and out offset each other. And then minus the stuff that's coming out, we have again 20 gallons per minute. And now we have to multiply by the concentration in the B tank, so the amount of salt in the B tank at any one time, which is indicated by A sub 2, divided by the gallons in tank B, which is 20 gallons. And we know that here the stuff that's coming in is offset by the stuff that's coming out, so we always have 20 gallons in the tank. Now we can simplify some things here. And what we get is A sub 2 prime is equal to A sub 1 minus A sub 2. So now I can write over here A sub 2 prime is equal to A sub 1 minus A sub 2. And then if I remember what the other color was, green, I can say negative A sub 1 plus 0 A sub 2 plus 40, and that's going to be A sub 1 prime. So now we can pick out, well, I forgot to put the ones here. Let me put them in so that you see. We can pick out what the formula for the coefficient matrix will be. It'll be negative 1 and 0 and 1, negative 1 right here. And then here we're going to have the forcing function, which is going to be 40 and 0. Now once we have this, they're telling us to find the complementary solution. So to find the complementary solution by hand, what we want to do is we want to find the eigenvalue of that matrix and solve the eigenvalue problem substantially. So the vertical lines indicate that we're going to take the determinant of what's inside, which is going to be this entry multiplied by this entry minus this entry multiplied by this entry. So if I factor out a negative sign, I'm going to get lambda plus 1 minus 1 and lambda plus 1 minus 1 times 0 equals 0. Well, that makes this part 0. These negatives cancel out. And here we just get lambda plus 1 times lambda plus 1 equals 0, which makes this lambda sub 1 equals to negative 1 and lambda sub 2 equal to negative 1. We have a repeated case. So with the repeated case, we're first going to substitute the lambda, and it's going to be negative 1 minus negative 1, which is negative 1 plus 1, which is 0. Here we have 0, 0, 1, and then 0 here. Once we have this, we know we have to multiply by A sub 1. Nope. We're looking for a K. K sub 1, K sub 2. We're looking for the eigenvalue, remember? And that's equal to the 0 vector. This is the eigenvalue problem. So now we're going to use the bottom one, and we notice that K1, K sub 1 is equal to 0, while K sub 2 can be anything. So let's say that K sub 2 is equal to T, which is equal to 1. Then we'd have 0, 1. Or we could have, and that's pretty much it, because there's nothing else that we can have it with that would be linearly independent from the other vector, because I could put any other number and I could reach that any other number by multiplying by that number essentially, because the other entry will always be 0. So we need to use this guess right here. We need to use the guess K sub 1 times e to the lambda 1 t times t plus p sub 1 times e to the lambda t. And to do this one, we have to solve another system, which is this. P sub 1, P sub 2 equals to K, which is K sub 1, K sub 2, which we said is 0, 1. So now we notice that P2 is equal to, oops. So now we notice that P1 is equal to 1. And well, that's good news because we cannot get a 1 by multiplying this by any scalar on the top. And P sub 2 can be any t. So let's say 1, and we have 1, 1. Or we could even say 0 if we want to, if that makes you feel cooler. So if that is 0, then we could write 0 here. And this would be our p vector. So our solution for this one, we'd have two solutions. X sub 1 is going to be equal to k, which is 0, 1, times e to the lambda, which was negative 1 times t. And then here you have to be careful. The solution involves both k and p. And the solution for k is going to be similar to x1, but we're going to multiply it by a t. And then we're going to add 1, 0, e to the minus t. So if we add it together, because they said find the complementary solution, where the complementary solution is going to be the linear combination of the two solutions that we found, we're going to have that the complementary solution is equal to c sub 1 times that first vector 0, 1 times e to the negative t plus c sub 2 open big parenthesis 0, 1 times t e to the negative t plus 1, 0 e to the negative t. And this would be our complementary solution. All right, the video is getting kind of long, so I'll see you in the next video for part C. And I'll show you how to do this in MATLAB at the beginning of the next video or in some of these video series. I'll see you next time.